Okay, so we can start. Welcome to everyone to this training session about the scientific computing service in CSUC. I will give you a brief presentation about the service, the infrastructure that we have here at CSUC. And after that, there will be different sessions about different topics. The second one will be about the Slurm workload manager, which is the system that we use to interact with the cluster. The third session will be about introduction to parallelization and performance optimization. Then we will do a short break. And after the break, we will have two more sessions. The first one about Conda, the Conda environment system, and how we use it here at CSUC. And the final one will be a brief introduction about quantum computing. Here at CSUC, we offer a lot of different services, but one of our foundational services is supercomputing. We have a long experience providing that kind of services. We are providing these services from 1991. And nowadays, we are one of the 14 nodes of the Spanish supercomputing network. And we offer the 20% of our computing capacity to this network. Here you have a picture of some of the different machines that we have had here at CSUC. And this is only for give you a brief description about of experience in this field. Where we come from, recently we have renewed with our infrastructure. Before the infrastructure that I will present in brief, we had this machine that was Pirineus 2, sorry, that had been purchased and installed in 2018, and it was a machine that you have here the description of the machine. It was mainly composed about standard nodes, 44 nodes. Then we had also some fat nodes and some GPU nodes, and two big shared memory machines. That machine was upgraded in 2022 with 19 additional standard nodes to give answer to the demand of resources that we had at this point. Where are we now? Now we have a new machine. That machine was purchased thanks to two tenders that we have done in recent years. The first one was in 2022 for 2,060,000 euros. And the big part of the machine was 3.4 million, and it was in 2023. These tenders have allowed the acquisition of an heterogeneous cluster formed by the following partitions. We have the big part of the cluster, which is a cluster based on AMD processors. This partition is a general purpose cluster based on EPIC CPUs, and it is a machine of 1.6 million euros. And this cluster includes fat nodes. Then we have the second big part of the machine, which is a GPU cluster, which is a cluster of nodes accelerated with NVIDIA H100 GPUs, and the value of the cluster is 1.4 million. And then we have the last part of the cluster, which is an Intel-based cluster, which is a cluster based on Intel Ice Lake CPUs. In parallel to the purchase of this machine, we had to do some adaptations in our CPD to this infrastructure. The two main novelties of this upgrade was the introduction of liquid cooling in the system and a large increase in resources devoted to GPU nodes. Well, I will give you a brief description of the AMD cluster, which is, as I told you, a general purpose cluster. There is no acceleration, there is no GPUs on this cluster. And it has 8 fat nodes and 50 standard nodes. All the nodes have the AMD EPYC processors with 96 cores, which is a total of 192 cores per node. And fat nodes have a total memory of 3 terabytes per node, which is roughly 16 gigabytes per core. Then we have standard nodes that have 2 gigabytes per core, and all compute nodes are diskless and use our Scratch system as input-output area for the jobs to work. And all nodes are interconnected between them and with the Scratch with an InfiniBand HDR network, which is a network that has a high bandwidth and very low latency, which is very suitable for MPI jobs. Here you have a summary of the specifications of the machine, and as you can see, we have almost a little bit more of 1,000 cores and a total computing power of more than 400 teraflops. Then we have the Intel cluster, which consists of 40 nodes in blade format, which allows to increase the density and basically save space on the racks. Each node has 48 cores with CPUs of Ice Lake generation, and each node has roughly 5 gigabytes per core. Those nodes are not diskless. Those nodes you can use the local disk, and you also can use the Scratch system. And as before, each node is interconnected between them and with the Scratch system with InfiniBand. Here you have the specifications of this partition of the cluster, and you can see that here we have 172 teraflops more. And then the final part is the GPU cluster. In this renewal, we have done a strong bet on accelerated nodes because we think it's important to have that kind of cluster for some new applications, like for example IA. Each node has 64 cores and 2 NVIDIA H100 GPU, and each node has also 384 gigabytes of memory, which is more or less 6 gigabytes per core. And as before, all nodes are interconnected using InfiniBand. And here we have the specifications of this part of the cluster, and you can see that here we have more than 1,500 teraflops, and we can see all the specifications. Here you have the difference between that last machine and the previous one, we have multiplied by 4 our computing power with respect to the previous version of Pirineus. And here you have more or less the architecture of the cluster. We have 4 different partitions. Well, right now we have only 3, but the 4th one will be available soon. We have 4 partitions: 1 AMD partition, 1 FAT partition for the FAT nodes, 1 GPU partition for the accelerated nodes, and the Intel partition, and the Scratch system, which provides the input-output area for all the compute nodes of the cluster. Here you have some performance and power consumption tests comparing the Pirineus 3 and Pirineus 2. And you can see that almost in all cases, the time of the different jobs is much better with the new machine, and the power consumption of the jobs is also better with the new machines. There is some small exception, but it's related with the execution of AVX instructions, which in Intel nodes uses AVX 512, and AMD nodes doesn't execute those instructions natively. Here you have some more tests, and now I will give a brief description that what you have to do if you want to access to our services. You can acquire one of the following packs of computational units, depending on your computational needs, and you can contract 50,000 hours. Here you have UCs. UCs is a unit that we use to do an equivalence between CPU time and GPU time, basically. You can also, well, you have here all the options that you have to acquire those packs. And as I told you, one UC is equivalent to 1 hour of usage of one individual core in a general purpose node. It can be AMD or Intel. And for computational time used in GPU nodes, there is an equivalence factor. So 1 hour of GPU usage is equivalent to 32 hours of CPU usage. This factor is valid for this year. Next year will be updated. And the system is quite simple. As users are executing jobs, the time spent by these jobs will be discounted from the total amount of time that the project have purchased. Apart from the computational time, we also offer different volumes of storage that users can use. You have the home, which is the user directories. In this volume, each project has this quota of 500 gigabytes. We do regular backups of these directories, daily backups, and it is not recommended to execute jobs that write or read data directly from home, because the connection is quite slow. Then you have the data directory. Here, each project has a quota of 2 terabytes. projects can ask for additional space in this volume, and we don't do regular backups of these directories unless you ask for them. If you want, you also can purchase the service of backup in this volume. And then we have Scratch, which is the space that jobs use to work, basically. Here there are no limits for the space of each project, other than the limitations of the hardware itself. There is no backup of these directories, and only jobs executing under Slurm can write on these directories. And files are automatically removed after 7 days of the end of the job. Then some notes about the working environment. The working environment is shared between all the users of the system, so all users access the same login nodes and the same partitions to execute their jobs. All nodes in the cluster use Red Hat as operating system. It's a well-known Linux version. All users access the system using the login nodes, and from those nodes they can interact with the cluster using the Slurm system. And login nodes cannot be used to execute applications. In fact, the CPU time for user processes is limited. So if you want to execute some very long job, it's better to do it under Slurm, because otherwise the system will kill your processes. And is not allowed to access the compute nodes unless you have a job executing on the node that you want to access. And finally, Slurm manages the computational resources of the system, the scheduling of the jobs, and also the accounting of used resources. As I told you, Slurm is responsible for managing the resources of the cluster. The user defines in their job scripts the resources that he needs to use. For example, number of cores or memory, the partition that you want to use, and the time limit of the job. The time limit is mandatory. If you don't put a time limit on your job, it will not execute. And using all the data that users specify on their scripts and some additional parameters that Ismael will explain in the following session, Slurm assigns a priority to your jobs and do the scheduling with having in account these priorities. And as I told you, Slurm is also responsible of the accounting of the resources consumed by the projects. Here you have the partitions that you have available in our cluster. We have basically 4 working partitions that are the standard, FAT, GPU, and Intel. And we have an additional partition, which is the Express partition, that is devoted to execute interactive jobs and short tests. As you can see, there is no time limit in any of the working partitions. And there is also no core limits in the partitions. But in the Express partition, you have a time limit of 1 hour, because it's devoted to do short tests, only to try to execute a job, to test if an input is working fine or not, or to execute interactive jobs. And you have a limitation in the number of cores also. You can only ask for 4 cores in this partition. About the applications that are available in the system, we have already a lot of different applications installed, but if any user needs to use an application that it's not installed, you can ask for the installation of course, of free software. There is no problem, but also of proprietary software if you have a valid license to use the software. We also offer different development tools. We have different compilers and different libraries and versions that you can use if you want to compile your own applications. And we recommend all the software that we installed, Python and R software is managed by Conda when possible. Sometimes it's not possible, but usually it is. We use Conda and Conda environments to manage all this software. We use private environments by default, but they can be shared between users or groups of users. The installation and configuration of Conda environments can be done by the users. There is no problem. But if you want, you can ask to the support team if you need help, and we will be happy to help you to install your software or to solve any problem that you find in the installation or configuration. And we are currently working in the integration of a container system. We are working on Uptiner and Singularity in our system to allow the usage of that kind of software also in the cluster. Here you have a small plot of the most used applications in our cluster. That data corresponds to 2024, so this year. And some additional information about the service. We have a portal, a web page, which is this one. Here you can find documentation, and here you can find also the support tool to contact the support team here at CSUC. We have documentation, as I told you, and you have the support page that you can use to ask for almost everything that you can ask to the support team. And I think that's it from my side. Here you have a picture of the HPC team here at CSUC. And if you have any question, I will be happy to try to answer it at least. You can put the questions on the chat or you can talk if you want.
Yeah, Adrian, just the usual question. Are we going to have access to the presentation at the end of the day?
Yes, of course.
Just to keep the data?
Yes.
Okay.
Yeah, we will send you by email. We will send the presentations for email, and it will be available also on the support page.
Perfect. Thank you.
In order to have access,
yes,
do we need to fill in some sort of formula?
Yeah, there is a form. You can find the form in the support page also.
Support page. Okay.
I did not talk about prices of the service because the prices for the next year are not completely defined. But in the support page, you can find the prices for this year. I think there are questions in the chat, but I cannot see them. Yeah. Well, Daniel asks if what happens if you exceed the computational time that you have. In principle, you cannot exceed the computational time because Slurm manages all the resources and it will not allow you to use more resources than you have. Martina asks, what is the application process for access to the HPC for academic researchers? As I told you, you have to access the support page, and there is a link to access the form, and you only have to fill the form and send it to us, and you will have access quite fastly.
So I access some website, but I might be in the wrong place because when I go to support, they ask for
hpc.csuc.cat.
HPC. CSUC.cat.
Yes.
Yeah, but then when I go to support, they ask for a user.
Yeah, you have to log in. Yes, you have to log in with an email address. Yes. But you can find information about the prices. You don't need to log in. In the documentation section is.
In the documentation.
Yeah, in the documentation you can find the prices. The prices are valid for this year.
Yeah, okay. Just to have an idea.
Yeah. Bernat asks, there's no backup of the data partition? No, we don't do backup of the data partition. You have to ask for the backup service. And are users usually keeping a copy of their data in their own systems? I don't know. That depends on the users. No, and Conda, the percentage of computing time used by Conda is by applications installed in Conda environments. So there can be a lot of different things under this category. When will you have Haptiner Singularity up and running? We hope that we had it soon, as soon as possible. We are working on it. And for academic research, are the costs sustained by the researchers or universities? Is there any differential pricing for academics? The prices that you can find in the documentation is for academic users. For commercial users, the price is different. And if the costs are paid by universities or by researchers, it depends on the institution. Docker, we don't have Docker, and we will not have Docker because the execution of Docker containers requires root access. So in principle, yes, we do. We use snapshots as backup. Yes.
Hi, good morning.
Good morning.
I have a couple of questions regarding time, because you mentioned that we can access an express partition to work 1 hour interactively, right? But just 1 hour? I mean, I cannot stay a whole day working in our studio remotely, for example?
If you want to long interactive job, you have to send it to the standard partitions.
But also interactive.
Yeah. You can execute interactive jobs in any partition, but the problem is that then you have to wait for the system to allow to execute your job. Yeah.
Okay, and what if I don't know how much time, for example, I want to send another job and I don't know how much time it will take. I don't know how much RAM it will use. I know few little of my resources.
You have to try. You have to try to do some tests to have an idea. Because the problem is that if your job uses more memory than
expected,
than expected, the system will kill you. Will kill your job. Yeah.
Okay. And well, also about the time, because sometimes it's not feasible to predict time.
Yeah.
And
yeah.
Is there any, like, I don't know, any threshold, like saying, okay, I said 1 hour is going to take 1 hour and a half, or I said, I don't know, whatever.
No, the time limit that you put in your job script is a hard limit.
But I can just say, okay, it's gonna take 10 days.
Yes, you can do it, but this will affect to the scheduling of your job.
Yeah, I can imagine that. Okay, thank you very much.
We have a couple more questions here in the chat. What is the level of protection of data against other users' access? In principle, we manage all the permissions using the Linux permissions. So you can protect your data by limiting the permissions of your directory. Storage and backup. What is the pricing for storage and backup? The prices for the next year are not completely defined, but you can find the prices for storage in, well, I will give you the link where you can find all the prices of all the services. Okay. Okay. Storage limit are hard? Yes. Is a hard limit also. You are charged for the actual time of execution, not for the time limit. Yeah, you are. Yes, exactly. You are charged for the actual limit of the actual time of execution. If your time limit is 10 days, but your job has only spent 1 day, you are charged only for 1 day. Yes. As you say, predicting time and resources of your job is difficult. Do you provide any standard way of predicting approximately this? It's difficult for us to give you a prediction of the time of your job, because sometimes we know that sometimes it's difficult to give a measure of the time of the job. There are situations in which it's quite easy, but there are a lot of situations in which it's difficult. As I told you, you have to test, and it's a trial and error process. Our recommendation is to be a little bit cautious with these time limits. Regarding data, then, can we use the system with sensitive private data? In principle, yes. In principle, there is no problem. We have not. We don't have the ENS certification for the HPC service, but we have it for other services here at CSUC. I don't know if this answers your question, but. Yeah, you see. Yes, user data are private. This is true. For your group. Yes. Regarding the time limit topic, what about the slurm option to increase the time limit when jobs are running? Users cannot do it. It's only an administrator thing. This.
Hello, I have a question.
Hello.
Well, two questions, in fact. First one, so if I asked for 10 days,
yes.
for how long will I need to wait to schedule my process, more or less? Because you said that if you ask for more time, you need to wait more time.
Well, now in the following session, Ismael will talk about that topic, but in principle, it depends on the occupation of the system.
But more or less?
Right now, the waiting time of the jobs is basically 0 because the machine is not very saturated. But it can change. This is something that can change. So it depends.
But could it be weeks?
No.
Okay.
No.
Okay. Days.
It can be days.
Okay. Okay.
It can be days. I don't know, 3-4 days.
Okay. And then if I ask for 10 days and I see that my process requires more time, can I increase the time? Or
you cannot do it. You cannot do it. That's the question that I just answered.
Okay. Perfect. Thanks.
Can we write to other storage partitions? We might. Yes. You can write in principle from any storage volume, but the problem is the speed of that read and write process. The optimal storage to write and read is Scratch, because the connection is through InfiniBand and then is very fast and the latency is very low. But you can also use data, for example, but not home. If you use home, the connection is very slow and the performance of the job will be strongly reduced. Is there a maximum time for responses to help requests? It depends. There are a lot of different requests. There are sometimes to install some applications, it's quite difficult, and sometimes we find problems that it takes time to solve. But in principle, there is no maximum time, but usually in a couple of days or 3 days, any request is solved, but there can be problems that are hard to solve. Can you cancel a job if you see time is not sufficient and resend a new job? Yes, of course you can do it. Yes. And if there are no more questions, we can pass to the following session. I will stop sharing. Sorry, there's one more question. Do you provide support for hosting virtual machines, web services, FTP services? Yes, those are services that are offered by CSUC, but not from the HPC department. But you can ask to CSUC for that kind of services. Yes.
No. El Jens tiene el problema de que no sabemos si va a querer hacer servicio o no. El Bernardo tiene el problema de que quizá acabe en operations. La Shin tiene el problema de que no.
Okay, let me share the presentation. Okay. So, good morning. My name is Ismael Fernandez, and I'm here to introduce you to Slurm. I want to do this session as interactive as possible. So if you have any question, do not hesitate to interrupt me and ask, and there is no problem. Okay. So let's start with what is Slurm. Okay. Slurm is a powerful resource management and job scheduling. Okay, if you have worked in other clusters or here in CSUC, you have worked with Slurm. And This system is commonly used for large and small Linux cluster. Okay, Slurm stands for Simple Linux Utility for Resource Management, or as some sorry, that someone the presentation stops by itself now. This one. Slurm stands for Simple Linux Utility for Resource Management, okay? Or as some prefer, is just a Slurm, okay? This system has become essential in managing resources efficiently across various environments in high-performance computing. Slurm has developed as a collaborative effort mainly by the Lawrence Livermore National Laboratory in California, in the University of California, with Schmidt MD, that are the developers of Slurm, the Linux Network X, the Hewlett-Packard, and the group Bull. Okay, Bull. I don't know if you know Bull. Before they were Atos, and now I think that their name is Evident. I think they changed their name recently, so now it's Evident. So, the Slurm primary function is to allocate resources for a certain duration of time, okay, and manage the job execution on clusters. It provides a framework to start and execute and monitor work, often for parallel jobs that require multiple resources working together. Sorry. As a job scheduler, Slurm handles a queue of pending work, resolving resource contention among users to ensure that each job is handled according to a priority and resource availability. It's important because there is always, in a cluster that is shared among different users, there is always more compute work to be done than compute resources available at any given moment. Okay. Of course, Slurm is part of a family of resource managers and schedulers. It's not the only one. For example, on this side, you will see in this slide, you can see the load leveler from IBM, the LSF, that is also another one that is very commonly used, the PBS Pro, that it's a payment software, I think, and other ones. Each of them has a specific strengths, but Slurm is very interesting in front of other alternatives because Slurm has a few notable advantages, like it's open source, okay, it's highly scalable and fault tolerant. It's open source because if you miss some features, you can submit your piece of code to the developers of Slurm as Shed MD, and they will review it and approve it if this piece of code is useful for the user community, okay, and it's well code, of course. It's also fault tolerant because it's reliable and can adapt to a wide variety of setups. For this reason, it's highly scalable. And Slurm is used around the world in many different organizations, like government laboratories, universities, and companies. And if you go to the web of the top 500 list of supercomputers, you will see that Slurm is widely used in practically 90% of the computers. Okay. If you have worked also in Mare Nostrum 4 or Mare Nostrum 5, you will you have used Slurm. Okay, so it's a proof that it's used in mostly everywhere. Well, if we take Slurm as a resource management, as a resource manager, what does Slurm manage? Well, it manages the hardware of a cluster. Okay, if we remember, as a piece of tip, the cluster is is a collection of many separate nodes, okay, servers that are connected via a fast interconnection. Okay, it may be InfiniBand or any other of OmniPath or whatever. And a node is an individual component of an HPC system. Okay, so we generally enter to the cluster using SSH, as you can see in the slide. Enter to the login node, okay, and then we use Slurm in order to talk or work with the compute nodes and the shared disk and the high performance shared disk that are the BGFs, the Scratch, okay, that Adrian told you before. We also have the partitions, okay? The partitions is a way of group nodes, okay? It's a logical group of nodes that share common specs, okay? For example, we have the partition, the standard, that are nodes that have AMD EPYC CPUs. Other partition have the GPUs, okay? And each of them provide different level of computational power, memory and storage. So here we also have the express, as Adrian told you, that the common spec is not the hardware common spec, but is a functionality. Okay, so if you need a job that very quick job, or you need to test some script, you can submit your job to the system to this express partition, and the job will run. Okay, so Slurm is very useful to use with these partitions to request exactly what we need. Okay, optimizing the resource usage across the cluster. Okay, for example, here a user requests 5 cores, 9 gigabytes, and 1 GPU to the Slurm, and the Slurm will allocate these resources for this user. How much time? How many time? Well, it depends, no? Of course, we are not sending only one job to the system. No, we are sending much jobs. So Slurm can use several scheduling techniques to manage jobs efficiently. Okay, the scheduling, you remember, is the process of determining the next job to run on the resources. Okay, we are going to see only two. The first one is the FIFO, first in, first out scheduling. Okay, that the jobs are processed in the order that they are submitted. Okay, but as you can imagine, this method maybe is not the most efficient way to handle jobs in a shared cluster, high performance cluster. No, for this reason, Slurm can apply the backfill scheduling, that it's called, that allows smaller jobs to fill in the gaps of the queue when there are waiting jobs that require larger resources. Okay. In this way, we can maximize the resource used while we are minimizing the idle time of those resources. Okay. This method, the backfilling scheduling, is based on two key parameters. The first one is the priority of your job, okay? And the second one is the time that the system expects that your job will be running. That this time is the time limit that you specify when you submit the job. The first one, the first key parameter is the priority, okay? So you as a user, you cannot control the priority of your job in global, okay? And is set by the system as a linear combination of different factors, okay? The most important one is the quality of service, okay? And the quality of service is the QoS that is linked basically with your account, okay? Your account can have a normal priority or low priority if you are a REST user, a class A, class B, class C, depending on your account. Okay, and this is the main factor that will give the priority of your job. Okay. Jobs with higher priority are likely to execute before jobs with lower priority, but it's not always the case, as we will see later. Okay. The second factor important in the priority are the fair share. Okay, the fair share allocates the resources based on the user's historical usage. Okay, and requested and depending on the requested resources. For example, if a user has consumed a lot of resources recently, their new jobs that are sent to the system might be deprioritized to balance the resource allocation fairly between among all the users and all the accounts of the system, of the cluster. Okay. The next one is the age of your job. The age is the time that your jobs spends on queue that are not running, okay, that are pending. So it's this value arrives to a maximum of when the jobs spend is queued in the system for 7 days, okay, and is not valid for dependent jobs. If you send a job that is dependent from the others, this value is not increased. Okay, so if your job waits on the system for 7 days, maybe there is something that it's not working as properly. Okay, and we can review and we can see what is happening. Okay, and finally there is the job size. Okay, the job size refers to the resource requested for the job. Larger jobs receive more priority regarding hardware resources, but not in terms of time. Okay, this factor allows Slurm to prioritize jobs dynamically. Okay, large jobs that maybe are difficult to backfill in the gaps, but they are balanced by this increase in priority. Okay. And finally, there is a nice factor that this nice factor is the only factor that you can control for your jobs. That is a factor that allows you to order your own jobs. Okay, it's an integer that is range from negative value to a positive value, and the lower the value. The lower values of these factors increase the job's priority. Okay, so you can establish a new priority in your own jobs using this factor. Okay, as lower is the factor, more priority has the job. Okay, so the nice factor of 0 is the standard, and it will use only the priority of that the Slurm assigns to your job. Yes. Is there any question about priority? If not, we can pass to the second key parameter that is important for backscheduling. That is the time. Okay, the time limit that is what you establish when you submit a job. Each job in a Slurm has a time limit. So the partition has no limit in time, but you have to establish a time limit for your job. And it helps to prevent any single job that monopolize a resource indefinitely. Okay. Is a question? No, it's another question. So it's important to be as accurate as possible when you submit a job. I know that it's sometimes it's difficult to be accurate, but when you submit a new job, use a time limit that it's big enough to assure that the job will not be killed by a Slurm. But once you have more or less the idea of the time that the job will spend, decrease this time limit. Okay. Imagine the situation that you are seeing in the slide. That there are 5 jobs in the queue, and a second user send a new job. Okay, this second user has a in this situation has a lower priority, and the only factor that are determining if this job will run before or after is the time limit that this user set in the submit time. Okay, so if the user place a time limit much larger than the elapsed time of the job, maybe this job will spend in queue at the end of the queue, okay, and will wait until the other jobs are executed. If this user, for the same calculation, sets a time limit that are much shorter than the other one for the same calculation, only changing the time limit, this job maybe can be backfilled into the gaps of the queue and be executed before. Okay, so we pass from a wait time of 7 hours or days, depending, to a wait time of only 1 day or 1 hour. Okay, only changing the time limit. Again, I know that it's difficult sometimes, even when you are submitting a new kind of calculation, but it's important to be as accurate as possible. Okay. Then just a little reminding about the commands that we use to connect to the system, because now I'm going to explain you how to launch, how to submit these jobs, and how the jobs are created. Okay. We can submit. We can enter to the cluster with the SSH through the port 2122, and we can transfer the files needed using SCP or FTP or whatever protocol you want to use. Remember that you have 3 main places to work on: the home, the data, and the scratch. And the scratch should be the preferable when you are executing jobs. Okay. So let's look at the job creation. When we submit a job, users create a Slurm job script. Okay, we are going to see the different kind of ways, the different ways to submit a job, but in all these ways we have to create a submit script. Okay, the first one is the normal one, is the batch, the batch job. Okay. Here we can see a little bit an example of a script. Okay. Here we can see that in this script we set the parameters of your job, such as the job name, the output file, the partitions, the task or the course, and the time limit. Okay. The only mandatory parameter here, I think, that is the time limit. So you don't start this time limit, this job, you cannot send jobs to the system. Okay. For example, this is these examples that I told you: the job name, the job's standard output file, that is not the output file of your calculation, but is the output file of a Slurm job. Okay, so if you don't redirect the output of your calculation to anywhere, the output will be printed here. Okay, the error file, the partition, the number of tasks, well, what you can see here. The other parameters, if you don't specify them, there are some defaults. Okay, that for a standard partition is 1 core and 1,100 megabytes per core. The FAT is 1 core and more or less 16 gigabytes per core, and the GPU 32 cores. That this is not a default, but it's a fixed number. It's a ratio fixed by GPU. Okay, if you ask for a 1 GPU, the system will give you 32 cores, and if you ask for 2 GPUs, the system will give you 64 cores. Okay. Then the second part of the script is what you are doing in your calculation. Okay. For example, a general structure that your script can follow is the first, you load the module. The second, you copy the inputs to Scratch and change the working directory because you don't want to work from home. Okay, you go to Scratch. The third, the execution of your calculation, of your application, and fourth, the copy of the outputs from Scratch to home or to the data volume, depending on whatever you want to store them. Because if you leave in the Scratch, if you leave your files in the Scratch, they will be erased after 7 days. Okay, and there is no possibility of restore them. Okay, so please be careful about your files. Okay, I think that there is a question. Is it possible to specify shared RAM memory files so that several jobs do not have to load the same memory to the same file to memory? Well, it depends. It depends on your application, basically. If I understand the question, is it possible? Well, the RAM, okay, the RAM is exclusive for your job. Okay, if I understand the question, the RAM is exclusive for your job, so you cannot share RAM between 2 different jobs. Okay, imagine you are online. Loads engine. Well, in this case, what you can do is something that we are going to see later. That is using the steps of a job, not a job because the resources that are allocated for a job are exclusive, and for security reasons, these resources cannot be shared with other jobs. So you have 2 alternatives: or you write your files to Scratch or to a hard drive, okay, or using the same job, do some different steps. Okay, I don't know if I answered the question. Module load is mandatory. Use module load. Well, this one, Adrian. Well, it's mandatory depending of your application. Okay, as Adrian is answering you. If you want to use the applications that are installed in the system in the cluster that we have installed, the easiest way is to load the module. Then the module set the environment variables and whatever it needs. Okay, but if you compile the application, of course there is no need of module load. Okay. Well, yes, Adrian has answered this. Okay, the next one are the steps. Maybe it's useful for you. No, I don't know. Daniel, I think. The steps are a subset of the overall allocation of the job. Okay, they can run sequentially or in parallel, and the division of the job is made into steps to make easier to manage the concurrent processes in a job. Okay, this is a very advanced way of execute jobs, and in generally maybe is not the best way. Okay, it depends on your application and your needs. More or less. So when you do a submit, what you are doing is require some resources for using a specified period of time. Okay. What you do with these resources is up to you. So inside the job, you run srun, as you can see in the example, and srun what do is make use of these resources. Okay, is a command from Slurm, and it's used, for example, for parallel applications. Yeah. So here we are saying to Slurm that we want to use some applications in some of them in some of the resources, and other applications or other whatever in other resources, but inside the same job. Okay, it's all inside the same job. For example, if we submit a job with 2 cores and we use these steps to run one application or one step in one core and the other step in the other core, we can do it in parallel, okay, or we can do it in serial. I don't know if I'm explaining. Yeah. So you submit one job, you execute multiple times, multiple applications, multiple calculations, and then you obtain only one job. Well, only one output. Yeah. Yes, Daniel? Okay. But again, this is maybe it's not the best way of parallelize. Okay, it depends on the application, but there is other better ways. Yes. Another way is the use of arrays, job Slurm arrays. Okay, you can use arrays. You can submit only one job. You can submit only one job and specify to Slurm that this job will be divided into identical jobs. Okay, and you will obtain this this number of identical jobs. Okay. So you submit once your script. Okay, this script submits different jobs, and you obtain the output of the different jobs. It's very useful. For example, well, job arrays. I don't know why it's no. Sorry, that. Well, wait a moment. That PowerPoint is doing strange things. Okay. Okay. So at the end, again, each of the jobs has unique task ID. Okay, but follows the same structure. So you submit a job doing one calculation, but changing, for example, the input. So with only one submit, you can work with multiple inputs. Okay, with arrays. Follow this. Well, each of them has the unique ID. So these arrays can be identified uniquely. Okay. This is very useful when you are running a collection of inputs, as I told you, like genetic data sequencing. Okay, like array indices, and this. The other one, the last one, is the dependency of the jobs. Okay, when you submit a job, you can submit another job and only allow the run of the second job when the first finish, okay, properly or had a fail or whatever. Here in the example, we submit 2 jobs, okay, A and B, for doing a preprocessing the whatever. Okay, we submit 3 more jobs that will do the analysis of this data, this processed data, and when the analysis of the data has end, then the last job, the job X, will verify the output of your jobs. Okay, it's very useful when you have different workflow that have different steps, and is it possible to use SnakeMake or Nextflow to control the submission? Yes, we have Nextflow installed. Okay, so Nextflow, in essential, Nextflow do this. Okay, so Nextflow, you send a job with one core to the system. Well, you know, maybe you know how it does work, but you send a job with one core to the system, and this job is a master job that sends multiple jobs depending on the workflow that you are running. No, so this is more or less the same philosophy, but yes, you can use Nextflow. Okay? But inside the Slurm, so you send a job to a Slurm that will run Nextflow, and Nextflow will send more jobs to the Slurm that will run the calculation that you need. Okay. Well, there are different types of dependency, depending of whatever you need. No, after the start, after the end, if the job ends correctly, ends with a fail. Well, there are multiple options here. So at the end, jobs can go through various through different stages in a Slurm. Okay, they go from pending to running. Okay, when you submit a job, they go from pending to running, then to completing, and finally to complete. Maybe in some cases you can find a job with a different state. For example, if the state is timeout or fail, indicate that the job has failed for some reason. If it's timeout, it's because your time is not large enough, and the Slurm has killed your job. Okay. Well, this is an assembly more or less, but is what more or less is what you will find in the cluster. So just to finish, we are going to see some important comments for Slurm to see all these resource manager, the scheduling, and the send of the job. No, for example, when you want to submit a job, the first one is use of sinfo to see what is happening in the cluster, how the nodes are, see if the partition is up or if the partition is down, how many partitions are, how many nodes are available, etc., etc. We can see the time limit of the partitions. This is with the sinfo of Slurm. Also, you can use the status command. The status command will give you the same information, but more nicely and more formatted. Okay, you can see at a glance what is the occupation of the machine. Okay, and the different partitions. So you have created your file, and you send your file to the Slurm using the sbatch command. Okay, the system will give you a message saying that the batch is submitted, and will give you a job ID. Okay, if you do an SQ with this job ID or with your name or with --me, will give you, for example, if you do it with SQ --me, will give you only the jobs that are your jobs. Okay, and here the important information is the state of your job, the why is not running if it's not running, and if it's running, where is running, and the time that has been running. Okay. Then while your job is running, if you do the SQ, you will see this information, the time and the node where it is running, and you can retrieve some important information from the job using the sstat. Okay, for example, the maximum memory used for your job, and the process IDs that are assigned to the and then whatever this is running, no, inside your job. Then finally, your job goes to the completing state. Your calculation just ends with an SQ. You see this. Okay, you see that the state is CG, that is completing. And finally, you can retrieve some historical information for your jobs using the SICCT. Okay, that this will print you all the information of your jobs, the state of your past and current jobs, and some more information. These commands are widely configurable, and you can format the output of the info that you want to obtain. And of course, if your job goes in a way that you don't expect, you can cancel the job for whatever reason, okay, with a scancel command. Okay? And if you do the SCCT, you will see that the state of your job is canceled, okay, because you cancel. So just for finish, remember that you have to choose first the most suitable partition. Use the Scratch as working directory, okay, during your jobs. Move only the necessary files, so move only the input files that you will use and the output that you will you need to retrieve. Not move. Please do not move all the files of your directories, because it's a spend of time for you and it's useless. Okay, and keep your important files on home or on data, but especially on home, because is where the snapshots are made. Okay, so if you delete some files for error, we are going to get them back. Okay. When a job fails, can you see why was it killed? Well, the fail status, it depends a lot about depends on your application. Okay, in some applications propagate the error that they do. Well, the reason why they end, no, and the state of the job is showed as fail. Okay, but some applications no. Some applications do not propagate the error, and simply they say that the calculation ends properly, and just it. Okay. Depending on the failure of your job, if it's a timeout, you will see that it's a timeout. If it's out of memory, you will, in generally, see that is out of memory. I say generally because it again depends on your application. For example, Gaussian is an application that in some moments when they change the file that is executing, okay, memory increase a lot. If this increase is sharp enough, maybe Slurm cannot detect this out of memory. Okay, the system kills the job, but Slurm does not know why it's killed. Okay, so the job maybe is has finally with a state of completed, but it really has been killed by an out of memory. Okay, so it's important to know your applications that you are running, and it's important to be aware of what you are doing. Okay, in order to know why a job fails. And well, that's it. If anyone has more questions about anything about the Slurm or the system, you will Christian will give you some examples of sending jobs to the system, and you will see in in vivo, no, whatever what is happening to the cluster in the cluster when you submit jobs. No questions? Okay, so just enjoy your Slurm because it's highly addictive. And thank you for attention. If you have any feedback or any problem, you can contact us through the portal, or if you have feedback about my presentation, you can write me through the email, okay? So let me end the presentation. I don't know how to. Si no, aquí, ahora sí. So, Christian, the floor is yours.
Thank you. Thank you, Ismael. I'm Christian. Can you hear me? Yeah. Let's show. So maybe it's a how-to. This presentation is a how-to on how to launch jobs to the queues, to the cluster, and maybe some advices in how your obtain the times, the memory requirements, the course. Okay. So let's start. You are here because you have a problem. You have a computational problem that, fortunately, you know how to solve. No, you maybe need the geometry of a molecule. You need the harmonic of a structure. You need to solve the orbitals of a molecule using Hartree-Fock, DFT, using molecular dynamics, and so. But when you try to solve in your own computer or your own workstation, you have a problem. In fact, you have three kinds of problems. Maybe that it spends too much time. Maybe you need too much time and it's impossible to solve in human time. Maybe your problem is too big and it cannot be allocated in memory. That's typical too. Or your data needs too much storage. For example, if you need to align a genome or so, and your hard drives cannot allocate that amount of data. Okay, what's the solution for this? Our typical solution, the engineer solution is, okay, if I need to figure something, I provide more cores, more memory, and more faster storage. Okay, that's what we have in a cluster, more of everything. Okay, so how we manage this? Ismael showed you the scheduler, but the scheduler only manages the resources that you ask. But how many resources have you asked? Okay, that's our problem. First of all, you need to know what is your lack. You are not enough compute power, you are not enough memory, or you are not enough I/O, performance in your disk or quantity. Okay, so first of all, you have to answer this question. Okay, in order to now to get an answer without using a profiler or a professional or IT tools, you can do three things. The typical things that you can do is, first of all, is if you use more cores and you get less time, it's compute bound. Okay, so you can solve your problem using more cores. Otherwise, if you're using more nodes or better memory, you get more performance using the same amount of cores. Is memory bound in general. For example, DFT, Hartree-Fock. And if you have a lot of data and you get results faster using better hard disk or more nodes, it's IO bounded. Okay, so that's why you use a cluster, because you can solve this kind of bottlenecks in a one solution. Okay. For this, we have three strategies as known as MPI, when you use multiple instances of your program working separately in different nodes in order to get the full performance of all nodes. That is a more versatile and more flexible. Okay. Other strategy is OpenMP, or the threaded parallelism, that's known as. Okay, for example, Gaussian, it's a typical Clustal for an element. It's a typical OpenMP strategy. These kind of strategies has a problem that cannot be used in some nodes, only in one node. So it's limited by the amount of cores that you have in a node. Okay, and the newest in some way strategy is the accelerated systems. For example, the GPUs. This strategy is kind of OpenMP, but in a higher order of magnitude, that use the computational power of a GPU that it's higher than a usual CPU to produce mathematical results. Okay, so in another place, in another way, you can use some libraries. Okay, because you don't need to know how to program or how to use the previous strategies, OpenMP, MPI, or CUDA, for example. Someone coded for you. For example, if we have the mathematical libraries, LAPACK and Intel MKL, math kernel libraries. We have Fourier transforms, for example, fastest Fourier transform in the West, or the CUDA fastest Fourier transform. Or if you need manage a huge amount of data or parallelize your I/O, use HDF. Okay, hierarchical data format. Okay. In summary, first of all, you have to know what do you need to parallelize. Okay, in general, is the solving algorithm. Then, how much resources do you need? How many resources? Okay, more memory, disk, and CPU. And then select your parallelization strategy. In general, this strategy is selected by the coders, not by you. In general, for example, if you use VASP, you can use everything of them because both MPI, OpenMP, and CUDA are implemented. But for example, if you use Gaussian, only you need in a first approximation OpenMP, and in some few cases CUDA. And if you use Linda, you can run in parallel. But for most of Conda, for example, Conda implementation from something, typically is OpenMP threaded. Okay. So now I will teach you how to write some Slurm code, for example, to launch the cluster. First of all, you have to identify the parallelisms. Okay. The threaded parallelisms, if you make a top in your job, for example, if you are in your computer, you have a test of your problem before launching to the cluster, and you are not sure that if it's a threaded, a process, or a GPU parallel, you can use the top command to have a clue. Okay, in general, the threaded parallelism has a performance in the percent of GPU more than 100%, and only in one task, as you've seen in the Gaussian, in the L904X. On the other hand, if you have a process parallelism, that is MPI, you have a lot of instances of the same executable. For example, that's a star CCM executable that is running in 8 instances, each one in 100%. Okay. That's at a glance and one way to recognize if you are in a threaded parallelism or process parallelism. Okay. So after that, you have to allocate or assign the amount of memory that you need. How? Okay, you can get it from top again. Okay, top say you how many resources or how much amount of something are you spending in each job. For example, Gaussian is spending 47 gigabytes of memory. Okay, so you have to ask Slurm the amount equal or upper of 47. On the other hand, the MPI parallelization creates a lot of instances, but each one needs its own amount of memory. So if you see, you 1.3 gigabytes, 1.3 gigabytes, 1.3 gigabytes. So you can access Slurm the amount of memory per CPU, 1.9, 1,900 megabytes, or you can ask for the total amount of memory. For example, in the case of Gaussian, 64 gigabytes. Okay. Here we have the amount of default of memory of each queue. The standard around 2 gigabytes, the GPU around 6 gigabytes, and the FAT partition around 16 gigabytes. Okay. So now, how many time? How much time? How many hours? How many days? A first approximation is if you have a previous test on your computers, the typical solution is make a linear extrapolation. If in your computer with 4 cores takes 1 hour, in a supercomputer with 2 cores, it should take half an hour. It's a more basic approximation. Obviously, it's not exactly because your computer and an HPC node don't have the same characteristics, but it's a upper limit to the time. Okay, because the time cannot be at first sight if you are don't make a test, it's impossible to guess. So, as I said, first of all, you have to identify the parallelisms, if it's serial, if it's threaded, if it's MPI or accelerated by, for example, a GPU. You have to estimate the amount of resources, how many cores, how much memory, how many GPUs, and try to estimate as better as possible the runtime. Because as more runtime and more cores and more memory you request, probably more time you will be in the queue waiting for your resources. Okay, that's a clue. As Ismael said, try to be optimal in moving your data, because you are spending time moving data maybe that you don't need. Okay. So one example, for example, Gaussian, it's an OpenMP application. For the first line, it's saying what's the name of your job, Gauss16 test. The output file, Gauss test, the %J, it's the job ID. It's a shortcut for the job ID. Okay. The error file, you will need one task because it's threaded parallel, and you will ask for 16 cores, one for each thread. You will send you to the standard partition, and you will need the total amount of 15 gigabytes. And your runtime will be 10 days for maximum. Maybe it will be take less. Now you ask the system that you will going to use Gaussian to set up the environment with module load Gaussian G16B1. And that's, from this moment, that's your real job. You set the input dir, home, Gaussian test inputs, your output dir, home, Gaussian test outputs. You change your directory to scratch where is your job ID. I later will see how. You'll copy your inputs and you'll launch on Gaussian. After finish Gaussian command, you create the output dir and you move your data. Okay, that's a typical OpenMP job in Gaussian. That this script is functional, so you could copy launching if you have the input. Your input is called input. It will work. That's a VASP example. Same structure. Okay, the job name, the output file, the error file. Now you need 24 tasks because VASP in this case it's MPI, so you need 24 instances of VASP using one core each one, and you ask for the memory for each one of these tasks, 1.5 gigabytes. Okay, and you will need 20 minutes. You load the module of VASP 544, and the same as Gaussian, you define your inputs and you launch your job with srun. Why srun? Because srun, it's a wrapper for MPI run, that is the way for launch MPI jobs. srun will get the information of the nodes and the cores allocated for you from srun, so you will not to provide it. Okay, it's automatic, and that's it. You will wait for 20 minutes for finish your VASP job, and you get the results. Okay. Another more difficult example: GROMACS. GROMACS is a molecular dynamics solver that it's hybrid. Hybrid seems that you can use OpenMP, MPI, and accelerated solvers at the same time. So you need to say to Slam that you are using a hybrid configuration. How? The number of tasks, in this case 32 tasks. Each task will take 2 cores to the OpenMP part, and then you will ask for 2 GPUs with GRES GPU 2. You will saying that you need 2 GPUs by node. In this case, you need only 2 GPUs because you are only in one node with the capital N. Okay. The second part is the same as usual. The module load your GROMACS and the srun command with your GROMACS executable and your GROMACS options. Okay. And then let's, I don't know if you have some questions until now, and now I'm going to share my terminal and show you how launch in real some. Okay, so let's. I'm going to stop sharing. Creo que puedo compartir. This and this. Okay. Can you see my terminal? No? Okay. So first of all, I have to join the computer. Vale. So I'm going to. Okay. First of all, I'm going to log in the computer, the cluster. That's what I have. Okay, the login message with some info, the status of the occupation. Okay, and now going to my data. Okay, data is set up for every user and it's your own path. Okay, in my case it's data CSUC convoyón. In your case will be data, your group, and your username. Okay, I'm going to my folder when I have 2 examples, NumD and VASP. Okay, I'm going to start with VASP. Okay. going to launch. Okay, if you see, I'm going to show you my Slurm script.
Tengo un problema con no están viendo la pantalla bien, no sé exactamente.
¿Qué veis?
Yo lo veo bien.
¿Y alguien no lo ve?
Sí. Solo una parte.
Oh. Maybe it's only a problem with your Teams client. Yes, I can. No. Okay, I'm going to show you the script. That's are my Slurm directives, the job name, bash test, the output file, error file. I will ask for eight tasks, 8 cores in one node, and the express partition because it's a small test. Okay, and I need a quick answer. Okay, I load my bash module 643. I say in my work dir it will be Slurm submit dir. That it's the Slurm submit dir is the place when I make I execute the sbatch command. Okay, and I will copy the 820 molecule to my Scratch directory. That is defined by Slurm at the moment I launch the job. Okay, and that's my run command, which bash. Let's go. So let's see. Okay, it's going to AMD AMD 01. So I'm going to do a top to show you how you see the execution. If you can then change the user, I only show my user, and that's only my. And I start Scratch. Bash test. Oh, wait. Let's submit a batch job to the number, and I can see my queue, SQ with SQ. If I do this, I see the queue of everyone. It's not that I want. I prefer to see my queue, and that's what I have. It's running in an AMD 01 with 8 GPUs. It's taking 21 seconds for the moment, and it's running in the partition express. As I said, I see some bash instances using 100 of CPU each one, as expected, and it taking 0.1% of memory. So around less than 2 gigabytes. Okay, it takes some. If I want to see my job running, I go to Scratch, and it's finished. So, but I can say it. I go to the job ID, and here are my results. Okay, that's my Scratch files, or all the files created by Bash. Okay, I go again to data. And see the results. The error and output file is created by Slurm. You can see that it should be the data showed by the terminal if it were an interactive job. Okay, so in this case, here are in a file. Okay, the output, the out card generated by Bash. And that's it. It should be the usual workflow of the flow of a job. Okay. Now, NumD. I will use NumD. I start with NumD because it's a CUDA application to see you how to launch in a GPU. In this case, it's quite different because Bash was a simple execution. Now I do some kind of scalability test. As I say if you are not sure how much time or how many GPUs do you need or how many cores, because it's the first time that you launch, you can perform a scalability test. That is, in other words, try some different configuration of cores, memory, or GPUs in order to get the fastest. Okay, so it's how to look like the kind of scalability test. Okay. I'm going to launch this command, an AMD3 with some CPUs and 2 GPUs, okay? 2 devices, 0 and 1, because we have 2 GPUs by node, with 8, 16, 32, and 64 cores, and get or choose which will get the best performance, okay? So I'm going to delete the previous outputs. That's it, and I'm going to launch. In the queue, I'm going to check where is executing, in which node. In GPU 2, so I'm going to GPU 2. Zero. And top. NAMD in this case is an OpenMP, so it's threaded. So you will see in this case 32 cores, goes 3,155% of GPU. That's a common NAMD. And if I want to check what is the performance of my GPUs, I use this command, NVIDIA SMI. And I have 2 instances of NAMD, 1 of each GPU, and now are performing at 6 and 5%. So in this case, because it's a much small problem, it's the example of NAMD, the Alanin example. I only using the 6% of each GPU. So I will, if I were strictly, or I would optimize my performance and my runtime at the use of resources, I will use in this case 1 GPU. But it's an example, okay? We are using 1 GPU that is spending 6% of each one, okay? In 2 GPUs, sorry. Again, now it's running with 6 CPUs in effective. Now it fired me, so it finished. I'm going to check my queue. Okay, it's empty, so it finished. My result for 16, for 32, and 64, and 8 cores. I'm going to make a tail command, okay, and NAMD out everything to check the time, the run times. Okay, with 16 cores, 30 seconds, 32 cores, 11 seconds, 64 cores, 68 seconds. Curiously, it's counterintuitive, and 8 cores, 13 seconds. So in this case, the best performance is around 22 cores. That's a scalability test. And that's it. I don't know if you, well, you can see the results in ACCT. That's my last jobs. For example, the last one was this, the BASP job completed. The difference between the BASP job and the NAMD jobs is that in NAMD, if you see, I use NAMD test SLM. I used 1, 2, 3, 4 times the srun command. For Slum, that's our job steps. And you see 1, 2, 3, and 4 instances of the job. In another way, only one use 1 instance of BASP in this run, so I only have 1. Okay, I don't know if you have some questions. No, there are no more questions. So, yeah, obviously that's an example. It depends on your it depends on you. Sometimes some applications, for example, VASP, if only you need one task or one core to each GPU. For example, NAMD can get better performance if you also use the CPUs in your computing node. It depends on the application. Obviously, if you only can't use the GPUs, again, obviously it's a waste of cores. Why you need 64 cores if I only need the GPU? But in some cases, for example, Gromax also use also the CPUs to the job, not only the GPUs. But for example, in other programs, you only need the GPU. For if you need 4 or 12 cores to the whole node, it would be enough.
When you try to allocate more than a percentage of GPU,
but you can do two things. You can use more nodes, more computer nodes. If because the memory per CPU, it's constrained by the total amount of the node. If your node have 100 gigabytes and you have 10 cores, the memory per core is 10. It's a ratio. If you need more memory per CPU, or for the GPU, you will use more nodes to get the desired ratio. That's the only way. If you cannot reduce your requirements of memory, you will get more resources from the cluster to set it. It depends. In some cases, yes. In some cases, no. For example, Gromax escalates really, really well. NAMD also too. VASP in some cases, in some systems, in some solvers. It depends on the application, the solver, and the problem. There is no an answer. You have to test it and decide if you'll get if your problem will degrade or not. There is no an answer. I think no one is writing something, I think. So finish.
So if there are no more questions, we will do a short break now, and we will be back at 12:15. So we are back, and we will continue with the training with the two final sessions. The first one is about LMOD and Conda on Pirineus 3. So Victor, the floor is yours.
Hello everyone, I'm Victor Perez, and I'm going to talk very briefly about LMOD and Conda and how to use them on our machines. I guess most of you are perfectly familiar with them, but just in case, we'll do a brief recap for users of Pirineus 2, pointing out the main differences in the configuration of both systems in comparison to Pirineus 2. And then I will show a basic usage of both, just to give you a basic idea of the capabilities of both systems. Okay, so let's start defining a bit what we are going to talk about for users of our previous machine, for previous cluster. And if you have used Pirineus 2, essentially we have changed the environment module system to LMOD, which is a re-implementation, which is different from the TCL implementation we used in the past. And we have essentially reworked the entire hierarchy in ways that will help us to better manage dependencies, compartmentalization, and so on. But for you, it should be essentially transparent. There's just some extra functionality that I'm going to briefly comment on. And then regarding Conda, the configuration is essentially the same as before. It's just that now your environments are going to be stored on data, on the data volume, and group-wide environments are available by default. And if you remember previous two, Mamba was not fully functional. Now we have full Mamba functionality implemented. So let's start with LMod, and let's very briefly discuss it. It's a Lua implementation of an environment module system which is fully compatible with the TCL classic environment module system that all of you probably know. And what it does is it allows us to pre-configure through files which contain a list of changes to the environment, to the user environment, I mean, some of the variables or other configuration values that we need to be able to run any application. And it is invoked through the module command. And in the LMod implementation, there's also ML, which is a useful shortcut that does some things as well. The easiest way to interact with it, it's to call the different sub commands of the module command. So for instance, module avail will show you all available modules, which it's not the entire ecosystem of modules, but it is the app level modules, which is to say, those are the modules that are going to load in order to be able to run an application. There are other modules that are loaded behind the scenes as dependencies, or there's a whole hierarchy of them. But in most cases, you will only worry about that app level module, which is going to configure your entire environment. There are also some compiler MPI library toolsets in case you want to compile and run your own applications, if you have your own code. And in general, we have every module is defined by an application name and a version. There's always a default version for each application. So if you just call for the name of the application, for instance, if you say if you call for the Gromax module, it will generally load the latest version that is available on our machine. And just briefly, if you use module minus the avail, then you're only going to see the default modules, which is to say you're going to get a list of the apps and toolsets that we have installed in our machine. To incorporate, to apply the changes defined by any module to your environment, you just have to module load or module add this module. You can load more than one at once. And the tree of dependencies will load automatically. You don't have to load the rest of the modules that are needed to run it. And also, the difference between CPU only and GPU modules is transparent to you, which is to say, you will have different versions of the module available for GPU and CPU environments, but for you, it's exactly the same operation. You just have to load it, and it will load the corresponding version. If you want to unload and undo the changes to your environment, you just have to module unload or module del those modules to revert them. Then you can at any moment show the modules that are currently active for your user using module list. You can see that by default we have a Conda module which is loaded always when you log in. The reason that this is contained in a module is that in case your application, for instance, has to use Python, and for some reason the version of Python in the Conda-based environment gets in the way, you can unload it. And then there are some other basic operations that you can do, such as you can module purge and remove all the currently active environments from your, modules from your environment. You can reset, which is essentially to go back to the default system one. So for instance, right now you will get an empty environment with only Conda loaded. Whereas if you do module purge, you will also remove Conda. You will essentially remove all the modules from your environment. And then you can ask for information about modules, specific modules, using module what is, which gives you a brief description of the module. And you can also do module show to see the details of what that module is going to do when you apply it to your environment. You can also search modules using module spider, which looks at module names using, you can use different approaches, and you can also look for modules by keyword. For instance, you can use module keyword GPU, and you will see only GPU compatible modules. And something that is implemented in LMod and was not implemented in our previous use of TCL modules is the use of collections. You can define collections using your current environment. For instance, if you load several modules that you want to use together, you can save the collection, giving it a name, and then load it all together and so on. But in general, they shouldn't be necessary because our entire configuration of the module environment module system is geared towards single module use. That is, you just load the top level module and everything below it will be automatically loaded. So in general, you should only need to use one module containing everything that is there to use. But in any case, there's also additional functionality that you might want to use. You can check the documentation at the link, and you can always contact us, and we will be happy to help you with whatever additional functionality you want to take advantage of. And with that, let's move on to Conda, which I'm sure all of you know it. It is just a cross-platform environment management system, which allows you to use binary package repositories to manage not only software, but also the interdependencies between different pieces of software. And it was started as a Python tool for scientific Python packages, but it has been made language agnostic, so you can find pretty much everything in there, including not only lots of R packages, Perl, other languages, but also system software that might be necessary to encapsulate to run that sort of software, that type of software, such as libraries, compilers, and so on. It is invoked through the conda command, but we also have Mamba available in Pyrenees 3, which is a conda-compatible alternative package manager, which has been designed in many ways to overcome some of the bottlenecks of Conda in terms of performance, both at the level of resolving environments and resolving dependencies, and at the level of downloading and installation speed, essentially. It's installed side by side with Conda. So if you have Conda available in Pyrenees 3, you have Mamba as well. Now Conda, since some versions ago, uses the faster libmamba solver library to resolve dependencies. So if you're using Conda now, you're using the core of Mamba. But there's also the Mamba executable, which further implements multi-threading and other little tricks to gain an advantage over Conda in terms of performance. In any case, because Mamba doesn't implement absolutely everything that Conda does, but if it doesn't, it calls Conda as a backup. So you can always replace Conda with Mamba. And if there's any problem, it will let you know. In most cases, it will simply use Conda to do it if Mamba can do it itself. So from now on, everything that I say about Conda, you can just replace with Mamba and you will get a faster execution. This is especially true if you are managing very large environments with many dependencies and you're updating or you are installing many different pieces of software at the same time. Mamba is just much faster. So what's the configuration of Conda on Prince 3 on our cluster? Essentially, we have that Conda module, environment module, that is loaded by default. So you don't need to do anything to have access to Conda, but you can unload it if it is needed, because there's some sort of problem with that environment being there. There's only one environment that is offered and shared for all users, which is the base environment, which provides the basic tools to allow Conda to run, to install software, and so on. And then the environments, the rest of environments are private, either at user level, individual environments, or at group level, group-wide environments, which are visible for all users in the group. Both are stored on the data volume at slightly different locations. So your personal environments will be located at data, your group, your username, .conda/envs. And for the group, for those that are available for your entire group, it's the same, just without your username in the middle of the path. You can use Conda env list to show a list of environments that are available. As you can see in the image, for example, base environment, which is on prod and is shared by all users, is always visible, but then you will have a combination of group environments and individual environments for your user. To activate an environment, you just have to run Conda activate, as you know, and Conda deactivate. Deactivates the currently active environment. And to see the packages installed inside that environment, you can use Conda list without the env that we saw in the previous slide. You can either specify a name of the environment, or if nothing is specified, it just applies to the currently active environment. Then you can create personal environments using Conda create -n and the name. You can either create an empty environment using this command, or you can specify the packages you want to be installed at first, up to you. To create a group shared environment, you have to specify the path. So it's slightly different. You use Conda create, but you specify the path with -p, and you have to write, unfortunately, the whole path. But once you've done this, you don't have to call it by the path, because the location of group shared environments will be visible to every user in the group automatically. Then you can also install packages in any of your group's environments. And of course, you can have a greater degree of control by specifying channels and specifying versions of the software. By default, every user has access, or rather, access to the defaults via Conda and Conda Forge channels is configured by default. Otherwise, you will have to manually specify the channel you want to use it, if you want to use it. And you can also update the packages. You can update all the packages in an environment. You can remove some packages. You can delete your whole environment, and so on. And there's also you can use revisions to have a have a history of modifications in case you want to go back to a previous version, something like that. And that's all. I'm going to show you very briefly an example of this. We're going to create a Conda environment, but if you are going to follow along with my colleague Alejandro, who's going to show you a hands-on tutorial on quantum computation in the next section, you might want to create in your own machine. It doesn't have to be on the cluster. It's actually better if you do it on your own machine. You can follow along with the software I'm going to install just to get your environment ready, because it's going to take a few minutes to install everything. So if you want to follow along, I invite you to open a terminal in your machine and create a Conda environment. So I'm going to show you the video doing this. Let me share. Okay. Can you confirm? Can you read my? No. Okay.
Compartir la presentación y compartir pantalla.
Let me very briefly. Okay. Can you not yet? Okay, let me.
Ahora sí. No.
I'm sorry about this. It's always the demo effect. Okay. Let me do this very quickly. Let me just show you what you have to do. Let me just copy the packages you need, because okay, it's working. Okay, finally working. Okay, so you can see it, right? Let's go through it. So I'm starting from my own machine. I'm just connecting to the pin 3, to the cluster. Okay. We can check that Conda is available. I'm going to use Mamba instead of Conda. I'm going to first create an empty environment. I'm going to call it KiboChem. I'm going to activate it. And then we need to install the following packages. We need Python 3.11. We need Kibo. We need IPyKernel, Matplotlib, KiboJIT, and Jupyter. And we will need to do an extra installation through pip, because the version we want for KiboChem is not available. The latest version is not available through Conda. So it will take a minute to resolve the dependencies and so on. We get the list of packages to be installed. You can see that it's quite a large environment, complex one. And because we don't want to wait several minutes for it to finish, I'm going to do as I do in TV cooking shows, and I'm going to show you very soon the effect, the final effect of the installation. My colleague is going to use a notebook approach, so that's why I suggest to run it on your local machine instead of on the cluster, because it's much more convenient to have it available with a graphic environment. And then we need to install KeyboardChem through pip. In recent versions of Conda is capable of tracking pip install packages, which is not something it could do before, which is also quite convenient. And those are the two install steps that you have to take to reproduce the environment for the next hands-on. And that's all. I don't know if you have any questions. We just have to wait until pip completes installation, and there are quite a few dependencies through pip as well. That's pretty much it. Okay, so I'm going to leave you with my colleague Alejandro. Oh, okay, sorry. Let me check this. Let me stop. Jose Francisco? Sorry, you're muted. Okay.
Thank you. Well, the thing is, I cannot write on the chat. I don't know. I'm not allowed to write on the chat, so basically, I'm just raising my hand to ask a question.
Okay.
You meant, because I get lost because you mentioned you were going to use local. I mean, you are installing in the
yes,
Pirineos, but you are going to use it local.
I show how to do it on Pirineos, but I suggest that if you want to follow along for the demonstration that my colleague is going to do, you do it on local, because it's going to be faster. So just reproduce the environment in your local machine if you have Conda installed, just because it's much more convenient.
Okay. No, because I was thinking, because there is like a way in Jupyter Notebook that you can connect, and I was thinking you were going to do something like that.
You can do that, but I think it's probably I mean, since I can only show you, and it's probably going to be a bit more difficult to make it work. Let's keep it simple. Let's do it locally.
Okay, thank you.
Thank you. So yeah, Alejandro.
Okay. Good morning, everyone. Can everyone hear me correctly? Yeah. Okay, thank you so much for being here. Thank you, Victor, for your very nice talk and for teaching everyone how to create the environment we will use at the end of the talk. I am Alejandro Jaramillo. I am a quantum computing technician here at CSUC for the Quantum Spain project. And today I'm gonna talk a little bit about quantum computing. Let me just share my screen. Guess everyone can see my screen now. Yes. Okay. So I'm gonna make a little bit of an introduction to quantum computing, tell you what is quantum computing, talk to you about one of the particular methods we use to do quantum computing, and then talk to you about an algorithm and show you a code that uses this algorithm to solve a little problem, just to show the capabilities of these kinds of devices. So first things first, the big question is, what is quantum computing? So quantum computing is basically using a technology that takes advantage of the rules of quantum mechanics and the strange quantum phenomena to solve problems in a different way than a classical computer can do. In some cases, not for every problem, but for some cases, this solution can be faster and more efficiently than in any classical computer. So just to make a brief introduction of the key concepts of quantum computing, this type of devices and technology allows us to perform new algorithms that are different and solve problems in a different way than a classical computer. Due to that it's quantum in and of itself, it's actually quite better for simulating quantum systems and measuring its properties directly instead of making really complex and hard scaling simulations or computations. This kind of technology is implementable in many different systems, such as photons or superconducting circuits or ultra-cold atoms, so it's quite versatile. And it's also compatible with classical computing. So as I said before, it's not better for every problem, it's better for some problems. So just like a GPU can solve some problems better than a CPU, a quantum computer can solve problems in a better way. So it's compatible, and it will just add new assets to a classical HPC sensor. Lastly, I would like to point out that there are many different ways to perform quantum computing or to use a quantum system to solve a problem. And today, the kind of way I would like to talk about is called the circuit model, which is also one of the most extended models and ways to do quantum computing. So here you can see what a quantum circuit looks like. It's actually quite similar to what a classical logical computer looks like and does. Here we can see at the left our unit of information, which in classical computing would be just classical bits, ones and zeros. And then we can see just a succession of operations that we can apply to our units of information to transform them and finally measure them to obtain a solution to our problem. Now we just have to put a nice hat to all of that and turn it quantum. And now instead of classical bits, our basic unit of quantum information is the qubit, which is any two-level quantum system, just like the polarization of a photon, or the levels of an atom, or maybe the spin of a crystal. And then we perform a series of operations to those qubits. We manipulate them using quantum gates. Here we can see an example of a 1 qubit quantum gate, which is basically a rotation and unitary operation on the qubit, and 2 qubit gate, which instead of just acting on 1, acts on 2 qubits, and it's fundamental. So we can ensure that our quantum computer is actually capable of performing any problem. Finally, we have to measure our system to turn this quantum information into classical information our computers can process and have measure different quantities and have an outcome of our problem. So just a bit of a summary. Mathematically, we have an initial quantum state, which would correspond to the ground state of our system. And then we take a unitary evolution of our system until we arrive to the desired state, then measure that state and process the information. These gates are, as I said, unitary operators, and then we can measure it and post-process it to obtain the results we want. I'm sure many of you may have heard of all the crazy applications that quantum computers can have, like solve the protein folding, or simulating super complex molecules, or decrypting messages. But those kinds of applications require really large quantum computers that actually can perform operations for a really long time, and then are resilient to errors. So it requires also error correction. So instead of giving you a big list of all those applications, I'm going to tell you about what a quantum computer can do today. So we are today in what's called the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum. So noisy because we don't have the quantum error correction we need. Intermediate scale because we only can control a few qubits, so in the order of the tens of qubits. And quantum, well, because it's quantum, right? So we can just solve small systems and applications that can tolerate errors, so that the quantum errors do not completely destroy our results. And I want to talk to you about two interesting applications. The first one is quite obvious. It's the use a quantum system to generate random numbers. Here you have a picture in which we have a photon with polarization that would be in a superposition of vertical and horizontal, for instance. And then we can use a crystal to separate the two polarizations. And every time one of the detectors makes a click, we can associate that to a bit, so a 0 or a 1. So in this way, we can have random numbers that are way better than anything that we could achieve with a classical system that in the end is just a pseudo-random number generator. So this is really useful for something like a Monte Carlo method that requires not only random numbers, but a really large amount of random numbers that are actually random. The second reason for quantum random number generators is to use them to produce cryptographic keys that ensure more secure communications. And the second application, and which is the one we'll be seeing in more depth, are variational and hybrid algorithms. These kinds of algorithms combine quantum and classical resources. So we have a part that runs in a quantum on a quantum device, and another part that runs on a classical device. And this combination and iteration can mitigate the impact of individual errors in the quantum part of the algorithm. The one I would like to talk about is called the variational quantum eigensolver. This algorithm aims to find the smallest eigenvalue of a Hermitian operator. So as any Hamiltonian that we want to solve, this kind of algorithm can find its ground state. It does it by with three different distinct parts. First, we need to create a parameterized quantum circuit, so a quantum circuit in which we can control and fine-tune the effect and duration of the gates on our system, so we can produce a family of quantum states, of wave functions that will act as a trial function for the second part of our algorithm, which is to measure that state and compute the state's energy or whatever quantity we're interested in obtaining and minimizing. And then we use the energy we measure using quantum hardware as a cost function for a classical optimizer. This optimizer can then update the parameters and the effect of the gates, so we can search a small subset of the Hilbert space, and we can make different trial functions and iterate until we find the smallest eigenvalue of our system and effectively solve the problem. It's really important to note that, as I mentioned before, this is a hybrid and variational algorithm. It has these first two parts in which we produce a quantum state and then measure it, which are happening in a quantum computer. And this will be way more effective than simulating it in a classical computer, because the size of our problem grows exponentially as we add more and more qubits. And then the second part of the algorithm is classical. It's just a classical optimization problem, which uses what we measure in the quantum device as a cost function. And there are many, really, a lot of applications to these algorithms. The first and most obvious is to simulate quantum system directly and measuring its properties more efficiently in quantum hardware that we could do by simulating it numerically in a classical computer. This can be used to obtain the ground state energy and the ground state wave function of hard-to-solve Hamiltonians in a classical computer. And a really interesting application is that we can encode really hard problems, so NP problems, into problems that are easy to solve by a quantum computer but will be hard to solve for a classical computer. And with that, we're going to start the hands-on. I'm going to show you how to code the VQE algorithm using the Kibo library, which is a middleware library that allows you to simulate and run quantum circuits. And then we're going to use this to find the equilibrium distance of a hydrogen molecule. So it's quite a small system. First, what we're going to do is to build the molecule using the KiboChem library, and then use a Hartree-Fock method to obtain the energy and build an effective Hamiltonian using the 1 and 2 body integrals. Then we will construct a parameterized circuit to produce different trial wave function and use the built-in VQE algorithm to obtain the energy. And finally, to find the equilibrium distance, we will iterate through different interatomic distances to find the one which has less energy. Okay, so before we start, are there any questions about quantum computing or what we are planning to do? Okay, in the chat, Ismail has sent a link to the notebook we're going to be using. It has some text already coded and some blanks that you can fill in to finish the code. Okay, so I'm gonna share my screen again. You can see my screen, right? Okay. So here I'm gonna use, yes, sorry, a bit bigger, and okay. So we're gonna activate the environment that we created before and open a notebook. Notebooks are usually the way to go for small quantum system and small and small circuits. So here we have the step-by-step process on how to solve this problem. So first, we import all of the important libraries we need. Basically, we import the VQE algorithm from Kibo, and we import some parts of the KiboChem plugin, and then just Matplotlib and NumPy for visualization. So what we need to do first is build the hydrogen molecule, and this is really similar to what libraries like the one by Google do. You just need to create the molecule by giving it all of the particles you want, all the atoms you want, and their coordinates. And we're just going to create the hydrogen molecule. at a distance of 0.74, which is approximately the tabulated distance for the equilibrium distance for the hydrogen molecule. Oops, of course, I forgot to molecule. Okay, so there seems to be a bit of a problem. Let me check. It would be a hands-on if there weren't some problems, right? Yes. Okay. Now we'll get there, I promise. I think it's here, right? No? Damn it. Okay, yes. Here and here. Nice, we did it. Okay. So what we did here is to build a molecule and then run the Hartree-Fock method. This returns the Hartree-Fock energy. This will be useful later to compare these results to what we obtain using a quantum computer. Now, what we do is build the Hamiltonian. We will try to minimize using the VQE algorithm. Here you can find a more detailed explanation of what this does, but basically what we're doing is computing the 1 and 2 body integrals and building a second quantization Hamiltonian, and then translating that Hamiltonian into something that qubits understand using something called the Jordan-Wigner transformation. But this quantum computer, this Kibo, just manages to do it all for you by with using this command. We are asking to build a Hamiltonian, and we ask it for it to be symbolic. Here, now we can print it and show what we're going to be sending to the simulation of the quantum computer. Okay, it's taking a bit longer than I expected, but we'll get there. Okay, there we go. So here, basically, what we're saying, what it's saying is that it has chosen the CPU to run the simulation, because right now we're not going to use an actual quantum computer. We're just going to simulate the circuit. This right here is the pseudo or effective Hamiltonian of our system that we will be minimizing. Okay. Next, we need to construct the ansatz, which is the parameterized quantum circuit. And we need to define a few parameters. First, we need to say how many qubits our circuit will have, and that depends on the size of the Hamiltonian. Here, in any of the terms, we can see there are 4 terms. So that's the number of qubits we're going to need, which is 4. And then we can say how many times we want to repeat the same ansatz, and that's just going to be 1 because this system is small enough. And then we're just going to use a type of circuit that's already predefined that is called a hardware efficient ansatz that basically uses the gates that are natively implemented in the system, which are just rotations and the controlled Z gate. So this is going to be the hardware efficient circuit with n qubits equal n qubits, and the number of layers should be n layers. Okay, and here we can draw the circuit. Here we can see all of the gates that are acting on our system. These are rotation of the single qubits around the Y and Z axis. And these are the control gates, which are the 2 qubits that basically what they do is create entanglement. So we have more expressive circuit, and then we can explore a larger portion of the Hilbert space. And finally, we're gonna construct our VQE object, in which we need to say which circuit will be serving as our ansatz, and which Hamiltonian, which matrix we wish to minimize. We need to tell the algorithm which are going to be the initial parameters for these gates, so they can start the search, which they're just going to be random numbers. As we can see, we're going to have 2 times the number of qubits, number of parameters. And our solution will be to minimize the energy of the Hamiltonian. And there's minimize. No, yes. No, there's an unmatched. Oh, here. And qubits. Oh, yes, sorry. Just missing a bit of character. And we're done. Here you can see that the VQE algorithm is completed. This is the final obtained value of the energy. And this is the parameters that produce this state. So now we not only have the energy, but we can reproduce the state just by inserting these parameters into the circuit, and we can make more measurements or more computations to study the ground state. And now here we just do this all over again, just looping for different distances and seeing which are which is the equilibrium distance by minimizing. So let me just copy this so we don't have the same problem again. Here, I want to place the first atom at the 0 and the second at distance t. Then we run the Hartree-Fock, create the Hamiltonian, and minimize and construct the VQE object, and then finally minimize. And the solution will be the initial state, just the random parameters. We can also specify which method we wish to use for the minimization. This is any SciPy minimization method. And then this is going to take a few seconds as this loops for every distance we demanded. We can find the equilibrium distance, which is 0.71 Armstrong, which is quite close to the actual result. And the equilibrium distance, the equilibrium energy, which is, as I said before, really similar. These are the same results we will obtain using a Hartree-Fock method. So this is the Hartree-Fock energy. As we can see, is basically the same result. And now, just to illustrate the result, I'm creating this plot that shows the ground state energy as a function of the intermolecular distance. And here we have a zoom between the 0.2 and 1 range. And this is the equilibrium distance, which coincides with the minimum. And that's going to be all for the hands-on, just a way of showing that quantum computers can be used to solve many different problems in different ways that a classical computer does. So if there are any questions, I'll be glad to answer them. Any suggestions too?
Well, if there are no questions, that training session ends here. We want to thank all the attendants for being here, and we hope that you find the session interesting for you and your work.